Okay.
You're so big, bro. I didn't have the good.
So on this one, you pretty much, if you have a fractional thing to start with, now here you gotta be careful. What happens here? Yeah. If you replace n with n plus 1, you'll get 2n plus 2 plus 1, you get 2n plus 3. Right? So basically, that number that's there next to the 2n, if it was 3n, it would go up by 3. Does it make sense? All right, blah, 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 blah. Okay, so it's really, the easiest mistake to make there is to write 2n plus 2 here. But you got to go brain, no, dude, that's not what's happening. I'm letting n go to n plus 1. Okay. This is going to be 3. And then here I just write the reciprocal of all this business here. What the shit? So then what happens? What about the n plus 1 squared and the n squared? N plus 1 squared and the n squared.
Same degree.
Same degree? So the limit of that ratio goes to the coefficients is 1. Yeah. Is that right, you guys? Let me say this again. I got a lot of shit happening in there, yes? I got a factorial business I'm going to worry about second. Yes? I'm going to find the easiest part of this. To be honest, the easiest part is the x's, but n plus 1 squared over n squared, same degree, so the limit is going to be 1. Okay. I like it, right? That's the old horizontal asymptote, 3 situations. Bottom degree is higher, goes to 0. Same degree goes to 1, or the ratio of the coefficients, blah, blah, blah. Top degree is higher, goes to infinity. Slant asymptote, but we don't give a shit about slant, we just want infinity, right? We don't care how it does it. So this goes to 1. Of course, the x's are the next, are easy. What happens with the x's? I just have 1 x left over. Now, what happens with the factorials?
2n plus 3.
This is the one that's got more terms, right? Or you know. Yeah, sure, Jeff. It has more terms because n hasn't gone to infinity yet, so I can say that has more terms. So I have to. Once you do this, it'll come back to you. You have to pluck off a few terms to make it match with the other guy, right? So what is 2n plus 3 factorial?
2n plus 3 times.
It's 2n plus 3
times 2n plus 1.
times 2n plus 2.
Then 2n plus 1 factorial.
2n plus 1, and that would keep going forever, so I don't want to write all that shit down. Of course, those go away. And then what is that limit?
0.
Yeah, if I let n get crazy big, this goes to 0. When is that less than 1? Always. So what's the interval of convergence?
Negative infinity, infinity.
Yes?
So the x, can it stay there? I've seen, we pulled it out in some examples earlier.
Oh, okay. We did an example already, which is why I wanted these two. If you've done these two, these are 2 examples of 2 extremes. We've done a problem where we do the limit stuff and we get to this point here.
Yeah.
And then you have to divide. And then this will be negative 1/3 to 1/3. Is that cool? And then you have to check the endpoints. So we did an example like that already. That's your standard thing that could happen. Yes? Is that all right? So it's not a question of me making the x stay. It's that it didn't go anywhere. This one, it went bye-bye because the limit of that is 0. So I don't give a shit what x is. Yeah. I like it. And whenever you do this ratio test, you take what you get and you say, when is that less than 1? So sure, if this is dependent on x, you could get an interval defined on finite numbers. If you get 0, that's always freaking less. Or if you get 1/2, that's always less than 1. If you get a number less than 1, the answer is all real numbers. Negative infinity to infinity. What does that really mean? Guys, what does that mean? If I put a 7 in for x, will the series converge? Yes, because we just figured out it'll converge for any value of x. Yes?
So if it absolutely converges, does that mean that it's might be a stupid question, but does it mean it's negative infinity to plus infinity? Like always?
says it's almost, but if you're doing something using this specific process, yes. Yes.
I mean, in terms of the
If
ratio.
it equals 0 at the end, or any number less than 1, then my interval convergence will be all the numbers.
I like it.
Which just means the power series converges for any value you throw in for x. The other extreme is part B. Part B, I knew how much you guys liked factorial, so I decided to put 2 of them in there. So I'm going to get, what happens to this guy?
2n plus 1 factorial.
Good, 2n plus 1. On the bottom, I just get n plus 2. And then I get the reciprocal of all that business. Is everybody okay over there? You guys good? All right, I'm not hearing anything, so I'm going to keep going. And then I do the same thing we just did a minute ago, but I got to kind of do it twice. So let me do the easiest thing first here. The x's, of course, just become x minus 2, because I lose n of them. Then I can rewrite 2n plus 1 factorial as 2n plus 1,
2n.
2n,
2n minus 1
2n minus 1 factorial. And I also have an n plus 1 factorial. Oh crap and a half. Here, let me. I do this to myself so often. Let me try that again. So, 2n plus 1, 2n, 2n minus 1 factorial. Over, what can I do with this guy?
n plus 2, and then n plus 2 factorial. I mean n plus 1 factorial.
And then I have 2n minus 1 factorial. I already did my x's, but too bad for me, I'm doing them again. Okay. You guys all with me? So we just had to do the factorial thing twice, because I had one on the top, one on the bottom. What's left here? So let's see, these die. These die. I lose n of these again. I just want to do that again for some reason. So I'll get x minus 2. And then here I get 4n squared plus 2n over n plus 2. You don't have to multiply that out, because what's that limit going to be? This is going to go to infinity, which is never less than 1. So does this mean that nothing works?
No.
You always have the trivial solution. And again, we talked about this before. If I add 0 forever, that's going to converge. It's amazing. Yes. So you always have. So in this case, what did I know from the beginning was going to work no matter what? 2. The question then was, and the reason we did this work was, can I get away from 2 at all and still have numbers within that still work? And here the answer is no. And the first one was, yeah, you can get as far as you want to away from the damn thing, and it'll still work. You guys with me a little bit? Okay. What about, is that all right? Any questions on that? Okay. Is this coming back? I know some of you guys, it's been at least a couple of semesters since you took out 2. Yes?
On the top, wouldn't it just be 2 n's?
Here, this one?
No, on the other paper. Because isn't it 2n plus 1 minus 1?
Okay, real quick. Just to really show you this. an is here. an plus 1 means replace n
Yeah.
with n plus 1.
Oh, okay.
So then you get 2n plus 2 minus 1 is 2n plus 1, yeah. So be really careful when you have the constant multiplier in front of the n. It's going to affect when you change it. You aren't just putting a plus 1 in everything. You are literally taking all the n's and making them become n plus 1. Which normally leads to us just adding 1, but when you have multipliers, oh shit, it's not going to just be 1 now.
And I just want to make sure, so then for our IOC for that problem, we wouldn't really have one, but we would say x equals 2.
Oh, this one?
Yeah. So
Yeah,
like,
the
like,
interval of
yeah,
convergence would just be a single.
would just be 2. Okay.
So what would the radius of convergence be?
0.
Yes. Because you don't get away from the center at all. I like it. Okay. Number 2 is interesting because I am guilty of this because so often we have to do this, but it's really interesting why. And I think I did say we took a derivative of 1. When we did it and it was n equals 0, we saw an n come down, so the first term would have been 0, so we just made n go up to 1. Which is really the reason why that happens. It happens very often, but it doesn't happen always. So this is a really good example, which is why Past Jeff probably put this on here. If I take one derivative of this, what do I get? I'm not even going to write this, I'm just going to write that. So let's just see, what do I get when I take a derivative? The
1/3 x minus
n
1.
comes down, pass it around. So you got 1/3 x to the... Now real quick, what would the first term of this be? Let n equal 1.
X over 3.
What would the derivative of this be?
1/3.
1/3. If I make n equals 2, I'm not going to get 1/3. There's no way this guy could be this guy's derivative because it doesn't start with the right place, yes?
Right.
So actually, in this case, I do not want to change where that starts. Just to show you, in a traditional one of these, like if I do this, let me do it more better. Nx to the n. That's a bad example. Damn it. You could do it, Jeff. Hey, so much faith in you. N plus 1 x to the n. There you go. Is everybody with me? If I take a derivative, I'm going to get n times n plus 1 x to the n minus 1. If I let n equal 0, doesn't this just become 0?
Yeah.
So then we go, why even include that? We just start at 1 then, because the 0th term is 0. So it's not wrong to leave it 0. It's just not necessary to leave it 0. Maybe. So when do you change this? When it makes sense. So this is the first derivative. So I'll just call this y so I can make y prime. What's the second derivative?
N minus 1 over 3.
Yeah, now it gets interesting. Now, so I get, n minus 1 comes down. X to the,
N minus 2.
if I let n stay 1, what's the first thing I get?
0.
So now I want to make
2.
2. I don't need to. It's not wrong to stay 1. It's just unnecessary, right? Maybe. So if I said, okay, add these numbers together. 0 plus, you're like, why did you even say 0? What are you doing? That's basically what that is, right? Yes.
Why is it not a product rule if it's 2n?
Oh, beautiful. You're like, I didn't even know I asked a beautiful question. What is the variable? What am I taking the derivative with respect to? X. X. You do not want to take the derivative of a summation with respect to n. Because the n is the summation's variable. That would get trippy. These power series are representations of functions of x, correct? Which is why that whole first thing we did, figuring out the interval convergence, makes sense, because I have a function of x, I'm like, what inputs make valid outputs for the series? That's the interval of convergence. So when I take a derivative, it's with respect to x. So the only variable, I don't give a shit what Cn is. They give you this monster thing, and I don't care. I'm just going to write it all again, because the n's going to come down, so all I care about. You with me? So taking derivatives of power series cannot be difficult. You can have a lot to write if you have this crazy big ass Cn, but it can't be difficult because you're just looking at the x piece. Everything else is a constant.
I know you kind of already went over it, I just want to make sure I understand. So then whenever we do get the first or the second derivative, our n will increase with our derivative? Like, because you went
Oh,
n1 and n2.
So again, like I said, very often it will.
Yeah.
Sometimes it won't.
We're ever going to go more over that? Like sometimes it won't?
Not really. It's hard to just make a general statement.
Okay.
So on this one, why couldn't I start the original at 0?
Oh, because we plugged it in.
Because if I started at 0, I'll get undefined.
Yeah,
So
okay.
I artificially had to start at 1.
Alright, and then
Which
that's why
kind of explains why the first derivative, I didn't have to start at 2 now.
yeah.
But I can't make a generalization out of that. There's a few different reasons why you might not have to change the index.
So it's effective because whatever n is, we can't have it undefined, so that's what we would change.
Yeah, so the original one started at 1.0 because otherwise it would be undefined
Yeah.
at first. But But when I took the derivative, that went away, and I could stay at 1. Maybe. You could always, when you take derivatives of series, you can do exactly what I just did. You could write a few terms of the series, take a derivative, and make sure that your answer actually gets those new terms, yes? Because that's what you're supposedly doing, is taking the derivative of that infinite summation. Does that make? You can always check your work. Just write a few series of elements, and then do the derivatives and make sure it matches with what you're claiming the derivative to be. Maybe. And obviously this is going to be huge for us because we're going to be doing a lot of derivatives because we have differential equations. We have y prime and y double primes. You're like, really? In this class we have differential equations? So, has anybody gotten to these? So let me say this. I don't think I said this directly. There are two things that could happen when you're trying to combine power series. You can either have to change the indices, and or you have to change the n. You have to shift the n. Those are two distinct things. There's a third thing that, and by shifting indices, I mean taking elements out. So you either have to pluck elements out, or you have to shift the n. What the shit am I talking about? I don't know anymore. Oh yeah. Guys. So the first thing you look for is why am I not able to combine these? Because they are not like terms. Is that simple? So the first thing I try to do is make them like terms. And the only way you can accomplish that is by shifting the index. What the shit does that mean? Well, when I plug a 2 in here, what do I get up here? 0, right? So couldn't I start at 0? And then this would just be x to the n. Now, do you see how if I shift this back to, everything has to overcome that? I want this to make sense. If I shift my index back to, everything that's there has to go up to overcome the fact I just took 2 away from everybody. I don't know if that makes sense. When I tell my students, I'm like, there's a bouncer, there's a guy at the door that takes $2 away from you. So if there's a cover charge, you got to make sure you come with 2 more bucks than you had to at first. I don't know if you guys were. So anyway. Yes.
So you're saying when you change it to n equals 0, x equals n?
No, careful.
X to the n? Because sorry, yeah.
Does everybody agree that, I need you guys to really get this, I don't have to start at 2. I could have all the same terms, and I can start at any damn number for n I want to. Just the relationships that are spelled out have to be true. Does it make any sense? So, whatever number is, go over there, Jeff. Whatever number is here, everybody agrees this is a number, correct? Tell me what n is, that's a number. Whatever number that is, it's got to be 1 less than whatever number that is. And whatever number's up here has to be 2 less than whatever number that is. Right? So as long as that relationship holds, I don't give a shit what n is. I can start wherever the hell I want to. We just traditionally start around 0 or 1, yes? I don't know if you guys are really with me or not, but if I make n start at 0, this can be x to the n. Then I still get x to the 0. If this is 3, I would get x to the first. If this is 1, I would get x to the first. So I still get all the same terms. What does this become, though?
2 plus 4.
Yeah, the n would become n plus 2, and this would become,
N plus 1.
my God, Jeff, will you ever give yourself enough room? I don't know. So this will be 2n plus 2, n plus 1, c sub
N plus 2.
n plus 2, x to the n. I like it. And yes, I gave you plenty of room on this. Sorry, no, I didn't. Too early. Let me stop for a minute. Now, to be really, really honest, I'm going to shift the other one also. if you had wanted to, you could have taken this down to n equals -1, because then what would that have become?
N plus 1.
N plus 1. See, then it would have matched. But I kind of like just to keep it x to the n. But you guys, the more you understand the motivation, the point of what I'm doing, the more you start to realize there's multiple ways to get there. I need like terms. That's my first thing. I need like terms to be able to add these damn things. There's multiple ways to get there. Yeah.
You can also take the first term out of the first one and just make it match the second one, right? Even if it's n equals 3 on the first summation, since the x's will equal, I'll probably go that.
We're trying to do all this symbolically, and it's really hard to keep track of. If you do it kind of like looking at a few terms, it's hard to keep track of what's going to happen to the general. I'm not sure if you're with me. I think I know what you mean, but
Yeah, doing the homework, I thought that worked pretty well taking out a term.
we will have to take a term out.
Oh.
And we do that to make the indices match. Okay. Let's just do this. Let's see. If I take, all right. Let me make sure this might help for what we're about to do. If I have a series. What's the first term of this series? Damn it, Jeff. Someday I'm going to learn. First term is 0. What's the second term of this series? Yeah, when I make n1, I'll get 2/3 x. Well, let's see, I'm tired, so I'm just going to write the rest of them. So what would this go from to? Because I've done 0, and I've done 1, yes? So now I'm going to start at 2. Does anything inside change? Hell no, nothing. There's no reason the inside would change, because that form is what tells you what the next element is. If I need the ends on the inside to change, I must shift the end. If I need the indices to change, do you see how the index started at 0? Now it starts at 2. So if I pull terms out, that's how I can make that change. Just that change. Do you guys see that? Maybe. The form will not change if I just take terms out. It cannot change, because then it's creating new things that it's not supposed to. That's the definition of every element in this series. So that form can't change just because I'm pulling terms out. That form will change if I change the definition of n. It's got to adjust because of that change, yes? You with me? So when I want to make like terms, that's shifting the n. If my indices don't match, I still can't combine them. So then I have to do the pulling terms out. Okay. And you're all like, yeah, this is sort of like pulling teeth, Jim. All right. So let's see, what do I get on the next one? If I shift that, I want to shift it. When I plug a 0 in, I get 1. So now how do I make this x to the n instead?
N minus 1.
N equals 1, right? So if I want to make the power go up, I make the n go down. If I want to make the power go down, I make the n go up. Now, personally, I wouldn't memorize this kind of shit. I'm not going to... It just makes more sense to me to say to myself, okay, 0 makes it 1, so therefore if I start at 1, it'll make it 1 still. Yay. And now these are like terms, yes? Then what happens to the c? It'll be c sub
N minus 1.
kick ass. And again, check yourself. 0, there it is, Jeff. 0 goes to C0. 1 would make this C0. Yay. So how many ways is there to set up a series that represents the exact same numbers? Infinite number of ways. Kick ass. Like it. So what's the one thing in our way now? There's only one thing that's in our way.
You pull out the 0 term of that.
The indices are not right. So if I just pull the first term off of this dude, what's the first term off of this dude? So we make n 0, what do I get?
4. to 2, and then
Next to the 0, right?
just, yeah.
So then I'll have plus, starting at 1 now. All right, now I've finally got these two series to a point where I can put them together. Okay. You guys are appropriately excited about this, Lucy. No, that would be inappropriate. Okay. So if I want to put these together, dadgummit, Jeff. You control what's happening up here. There you go. So I got 4C2. So now I just got to pull out. So now I've got my 2, n plus 2, n plus 1, cn plus 2 plus cn minus 1 times x to the n. I don't blame you if at the moment you're like, what does that mean? So, didn't I just construct a new cn, basically? That's dependent on these other two c's. If I'm going to solve a second order DE, any answer I get should have, for a homogeneous second order DE, how many c's should I have in my answer? 2. I should have a C1, C2, or a C0, C1, or whatever the hell I'm going to call it. I should have two distinct C pieces, yes? Like C1 cosine x plus C2 sine x, that kind of thing. We're going to see the same thing happening with our power series answers, which is why I've got two distinct C's there, yes? Okay. So let's do this. Did I finish this? No, damn it. All right. One more. This will be the same thing. Anybody try this one yet? I desperately, okay. Let's do this. We'll do that next time. I have got to show you an example of what we're getting into. And this is just me always fighting against the clock. I agree. But it would meet like one day a week. I personally think that would be amazing. Or we really should teach this class over the summer. Yeah. So just to make it really clear, the quiz Thursday, we'll do systems of differential equations and this kind of stuff. That's from 6-1. Okay. Nothing to do with this. So, let's see. I kind of want to cut to the chase here, but a few definitions. So, real quick, I want to plug something. There is a, one of the best courses I ever took was called Mathematical Foundations for Physics. It was like Math 621 or whatever the hell it was. And I learned all this shit that I never learned in a math class that was specifically very useful for physics applications, right? One of the things I learned was how to integrate across the complex plane. Does this sound great? Okay, I like some of you guys are like, yeah. These kind of words you'll see all the time. So you can integrate functions that across the complex plane, and it's easier than it sounds, that you could never even imagine to integrate the way that we do them, right? So a lot of the terminology that we're talking about here, and what's funny is, I need to remember to bring this in because the book does go over this, I always forget it does this. There is something to be said about complex stuff that goes along with this. So that was a long thing. Just look up integration over the complex plane. if you're interested. Yeah, it's fun shit. So we call a function analytic at a point if you can actually construct a power series around that point. So I can construct, it would be analytic at A if I could do x minus a to the n, summation Cn x minus a to the n. If I could construct a power series around that point. For the most part, what that means is it's continuous through A and it's infinitely differentiable at A. Because how do you construct a power series? How do you construct a Taylor series, which is a form of power series? How do you construct a Taylor series? You're given a function, then what do you immediately do? You guys remember? Just start taking derivatives like crazy, right? F prime, F double prime, F triple prime. You guys kind of with me? And then you're trying to find a pattern so you can set up the general thing. I don't know if you guys remember. We're not going to suddenly start doing that. Don't freak out. Be like, I was told that was in my past. Yes, for the most part. It is. Obviously, all the nice functions we're talking about are good, right? Any polynomial is automatically good. Is any polynomial infinitely differentiable? Of course it is. X is a polynomial, yes? What's the root of x? What's the root of that? What's the root of that? Can you keep going? Alright, so let me ask again. Is any polynomial infinitely differentiable? Yes. Okay. You guys with me? Maybe? What's the Taylor polynomial that relates to x plus 1? X plus 1. Sorry. Maybe? You guys want to shut up, alright. A point, so it's analytical point if I can construct a power series around that point. And we know several functions that are obviously automatically analytic at certain points. We know their intervals of convergence over. A point is said to be ordinary point of this dE that should look very familiar if both of these functions are analytic at that point. So a very simple example of, let's look at some of these examples I got down here. If it's not ordinary, we call the poor little dude a singular point. All by myself. Okay. What's P of x and Q of x here? 6 and negative 7. Are either of those having issues anywhere? Are they discontinuous? Are they not differentiable? They're beautiful. So P of x and Q of x are 6 and negative 7. Are there any singular points? Are there any points where it wouldn't be infinitely differentiable and you can't make a power series? No, that's good. Cool. Any constants did you ask? What about cosine x? This next one. So obviously, I'm kind of giving the game away. P of x, Q of x. These are two that are in the list of known good things. Are there any singular points then? No, these are good for every point. Yes? What about this one?
1 over x, 3x.
What's wrong with the form I've given you?
Selenium coefficient.
I got to divide by x first,
Yeah.
and then automatically, what's thrown out for a very, very simple reason? Yeah, so where's the singular point? X equals 0. Okay. P of x would be 1 over x. Q of x would be 3xy. I'm sorry, 3x. So you can see a shortcut now. You know this is going to be divided. So what are my, what's P of x?
X over x squared minus 4.
And Q of x.
Negative 1 over x squared minus 4.
And what are my singular points?
2 and negative 2.
2, negative 2, I love it. So the functions, the differential equations we're going to be looking at, especially in section 6.2, are going to involve polynomial coefficients. So their singular points really don't have to be thought of in terms of can I make a power series. It's more thought of in terms of is it freaking continuous or not. Because if it's continuous around that point, then it's golden, right? If there's points that it's discontinuous at, then it's got problems. You could also run into, did I put a problem like that here? No. What if I had one that was like this here? Yeah, y double prime plus the square root of xy minus prime, Jeff, minus y equals 0. Is square root of x, so I'm thinking about x equals 0. Is x equals 0 an ordinary point for this? Is square root of x continuous at 0? Yes. Because we don't hold it against a poor little function if it's not defined on one side, then we just talk about continuity from one direction, yes? So it's continuous at 0. Are the derivatives continuous at 0? What's the derivative of the square root of x? 1 over 2, yeah. Okay, derivative of x to the 1/2 is 1/2 x to the negative 1/2. So it'll be 1 over 2 square root of x. Is that continuous at 0? Nope. So where would the singular point be for that? Or what's interesting is 0 is the only point that could even be a singular point. Does it make sense? What's the domain of square root of x? Including 0 to infinity, correct? Keeping things real, which we want to do desperately. Can you imagine diffie with complex numbers? We already had some of them, but I mean, like, you know what I mean? So keeping it real. The only possible points that could be considered would be 0 to infinity. So what's the only singular point? 0. Because it works in the function as it is originally, but it leads to non-differentiability. It's not differentiable at 0. You guys kind of, one way to think about differentiability is the derivative must be continuous at that point. That's the way to think about differentiability. Okay. Differentiability. Now, if I do have an ordinary point of a DE, we can always find, and specifically a second order DE. And we already know this. We already know that we can find two linearly independent, and we have to find, there must be two linearly independent solutions. Now what's really, really cool, let me see. I wanted, good, I think I have enough time for this. I want to do an example, stop doing that, Jess, of a problem that we already know the answer to. Because then we're going to get a series solution, but we can see the series is the series for that function. So let me just do it and see what you guys think. I did it somewhere, but I can go to it. Okay. I need paper. Here we go. Where I put it? Oh. So what about this here? Can anybody just tell me the solutions to this? Yeah, what would the, well, let's see, what would the ox be? So I should get C1.
Either X.
I like it. All right. Now, real quick, yes, sure. Just to remind you guys, does anyone remember what Sinchikosh?
Some shit with an E.
Good, hyperbolic cosine. So, inside. Very quickly, does anybody feel like you've never heard of hyperbolic trig functions? Okay. What's really funny is you can have a very conceptual view of them. Our normal sine and cosine are built off of what shape? Circle. So if I build the idea of sine and cosine off of a hyperbola instead, I'll end up with hyperbolic trig functions. You guys kind of with me? Same way that if you rotate a circle, if you go around it, you can build the sine and cosine function. If you start with a square, you can then build a similar kind of function. It won't be sine and cosine. So you can have different shapes that lead to things that are related to our trig stuff. It's just when I use a circle, we end up with our like regular trig stuff. Yes? Okay. All that stuff is beside the point. The more nuts and bolts thing is all these are combinations of e to the x and e to the negative x. That's it. So you kind of had a conceptual idea of hyperbolic trig, and then you had this, I keep getting all this shit, this e to the x minus e. Let me just make a functional form for that so I don't have to keep writing all that shit out. You guys kind of follow what I'm saying? So sort of like developed all at the same time, both directions. There's so many problems that come out with these kind of solutions, I can write it in a more compact form. in these hyperbolic trig forms. I guess semi with. If you've never heard of hyperbolic trig, there's obviously a little more to it than what I've just said, but that is the fundamental idea of what they're built on. So everybody with me? Okay, so let's keep that in mind. So, to solve this, now, I really want everybody to understand. This is solved, correct? We're done with this damn thing. I'm going to use the power series solution method because I already know the answer. So we can kind of check the answer at the end. Y'all with me? Obviously, I can use the power series solutions method to solve differential equations that there's no freaking way in hell we could do in any other damn way. You guys kind of with me? So I like to do a problem where we already know what the answer is, use the process, and then we can see. And then I can use the process on things that there's no other way I could get the answer. Are you guys kind of with me? So there are differential equations that there's no way to get the answer unless I use power series. Okay. So let me see if you guys are cool with this. And to be really clear, I'm going to build it power series around 0. So I'm going to have this assumption. So this feels kind of familiar to us, right? We assume the form of the answer and then we're going to throw it in and see what it leads to. We've done this kind of thing before. Can you guys really quickly do y prime, y double prime? Because we need the second derivative to throw in there, right? Oh, is it here? It is here. All right. So what do you get from y prime? So now I can start at 1. And also, another thing, well, all right, you also got to be careful about the fact, if it's 0 and this wasn't here, this would start at x to the -1. Yeah, so that could be another reason why you want to do something. But here, we start at 1 because the first term would be 0 anyway, so it almost doesn't matter what this guy would be. Yeah.
Why are we moving the project from x equals 0? Is it always going to be?
No, it won't always be. So that'll be part of what they have to tell you about. And that's why we were talking about like power series around x minus 2. So they have to tell you what to build it around.
Oh, okay, so this is like something that they tell you.
Yes.
We're not just saying.
Most often we're going to do Maclaurin. And remember, Maclaurin is the 0, just 0. Right, just around 0. Taylor series is the general, it could be around any damn point that I want. Okay, I like it. So y double prime, you just get crazy. And now you just throw stuff in and you kind of say a little prayer to your favorite math god. So, do you guys understand how very quickly this is going to become a problem directly related to everything we're just doing involving shifting the ends and making like terms? Because when you plug all this stuff in, you're going to have to combine them to get a single series. So if I plug this stuff in, there's y double prime. Now real quick, we will do some other ones, obviously not today. If there was an x in front of this, wouldn't this just go up by 1? Is that cool? So we will have some where there's x coefficients. And if there are, I just multiply them and that just goes up by 1. That's almost too nice to believe. It isn't here, so I'm not going to do that. All right, so I know on one level it sucks because it's Power Series, right? You kind of felt like you escaped them before and so forth. So now they're back, of course. But on another level, we've already done this shit. We've assumed the form of answers. We've plugged it in. Then we just kind of see where it leads. That's exactly what we're doing right now. Can anyone tell me how can I combine those together? What do I have to do?
Match the get like terms.
Not take out some terms, because the very first thing you always want to focus on is make like terms. Taking terms out will never change the form of what's inside. Let me say that again. If I take terms out of a series, it will never change the form of what's inside.
But if you take out the first two terms and then like right here, you replace it with an X variable, that's kind of what the book says to do, and it works pretty well.
Do it again, sir.
Yeah, like exactly what I did right here. Basically, you take the first two terms out, use some series one. It's basically watching it by what it ends up equaling instead of what it currently is in the series.
Oh,
What
so it's
X
gonna,
ends
okay,
up
okay.
equaling on the way
Yeah,
out.
you can tell how much I looked at the book for this. No, I'm sorry. So there is another method apparently
It works pretty well.
in the
It's
book.
a little
This is the way that I've done it forever, so I'm a little stuck in it, to be honest with you. But the book apparently shows
pretty
same math, but it's probably just turned around.
exactly.
Yeah. But the way I was taught, the way I immediately think of this always is I first make like terms, and then I start picking terms out if I need to. If you look at the book, you can do it a different way if you like the book's method better. And I couldn't show that to you right now because I don't even know what it is. But so if I'm doing it this way, how would I change things? Currently, when I plug a 2 in, I get a 0 up here.
So you drop the n.
So if I make this x to the n, this will become n equals 0. So see how n went up by 2? That's got to happen everywhere, right? This would be c n plus 2, n plus 2, n plus 1. Is that cool? And then I've got minus. Now here I got lucky. Because are my indices the same?
Yes.
Yeah. So I got a little lucky. I didn't have to also change the indices. So I'm really curious the way that that other way would work here. Yeah. We'll see. So everybody's with me right now? So again, this is a whole other set of skills you have to kind of develop, right? So you could be on the film, so I got a particular stuff. So you have to have this ability to work with power series. And the math involved is not that hard. It's just not, we're not used to doing it. Can I combine these now?
Yeah.
Yes, so I get the sum. Now I basically just pull an x to the n out at the end. Jeff, you can do it, buddy. There you go. Now, this statement says that this series that I've currently got written down is 0 always. That's what it says. One way to make it 0 is if x is 0. Does x have to be 0? Nope, it could be whatever the hell it wants to be as far as we know. So what's the only way to guarantee that this sum is always 0 no matter what x is? This has to be 0. Or alternately, okay. Damn it. Sorry. I just never have the time. Now this part, understandably, could possibly drive you a little bit crazy. But what we have to do, so now all right. Let me do a couple of the first few steps. If n is 0, so this leads me to this fact. Does everybody agree? This is a fact. This must be true. So if n is 0, what does this say? So this must be true no matter what n is too, correct? So let's see. Okay, let's make n 0, because that's where I'm starting, correct? So what would this say? If n is 0, C2 equals C0 over 2, 11. That's fascinating. So what if n is 1? Six, yeah, right? If n is 2, yeah, and the funny thing is you got to be really careful because it's so easy for your brain to look at this number, but just keep looking at 2. So it'll be 4 times 3 is 12, I love it. But don't we already know what C2 is? Is that cool? Isn't C2 C0 over 2? So then when I divide by 12, I get C0 over 24. Is that all right? Do you see how everything is going to be dependent on how many C's? 2. Everything's going to be dependent on C0 and C1. Do you see that? So, of course, I could keep going, but, I mean, I'm already over time. Of course I am. Why wouldn't I be? Just the bane of my existence. I desperately want to finish this because I want to show you we will get sinh and cosh. And if I get sinh and cosh, doesn't that immediately relate to these? Because aren't sinh and cosh just combinations of these two?
Yeah.
So if I get sinh and cosh from this work, I got this answer. And that, and by the way, I don't think I said that. It's hyperbolic sine is sinh, hyperbolic cosine is cosh. That's how you say it. Right. All right, guys. Yeah, don't forget quiz. Quiz on Thursday.
Professor,
Yeah.
you mentioned that integrating across the
Complex plane.
complex plane. So is that like two? So I understand like integrating on different planes from complex. So if I understand that,
Well, it's not. So it's more to do with we did line intervals, contour intervals. We did line intervals, right? So in my head, I've got the little diagrams in which it all. So we have these singular points, and we have to integrate around them in the complex plane. So we have these intervals that are impossible to do otherwise. It was one of the trickiest things I ever learned because really my brain went. Because you have these intervals where people just say, yeah, you got to do that numerically. And then you get to this, and you're like, oh, I can just go around the problem. It's the coolest thing in the world. I'm not sure what else to say about that.
so would I be like with the level of math that I have now? Would
I think you should know enough. You should be able to pick up. Off the top of my head, I think something else weird, but for the most part, I think you should be able to pick it up. There might be one or two things that deal with. I remember now. It's been a while since I did one. But yeah, look it up. See what you can. Oh yeah.
So, appreciate it. I got an extension on these assignments.
Oh, yeah.
I was struggling with, but for some reason when I go on to work on them, they like won't let me actually do anything. So
What's it say?
it says you get this pass for some reason. It says so when I tried to go like to
Oh,
do some
no.
stuff, it won't let me input it. But it did
That's
say.
the section that says I give you the extension.
Yeah, because on all these it says like here so it has to these it actually says.
Well, that's the problem too. There, it should show external science.
Well, it should, right?
Extended until when though? 20.
Well, that's when I think that's when I requested it because
What is today?
well I requested it for May 20th. Maybe that's what it is.
That's
I requested it on May 20th. Okay, so May 20th.
Should be.
Nothing else. Sorry. Yeah.
That was my fault. I just clicked on the wrong one.
Okay, cool.
Sorry, man.
No worries.
This,
All right.
Pretty much that's why I give it one.
what is this? You're gonna have some?
No. So you're one of those, so you know what you're missing.
Okay.
Yeah, I don't have to go in and collect all it. It really depends on this, because that's, the tests are heavier weighted than anything else. And also, you did corrections here, right? So obviously it's higher now. I can even do this
Yeah. That was fun.
here.
I love that.
Wait.
I'm not very good with the homework. How much? What percent of the grade is that? Like 10 or more?
The funny thing about homework is it ends up being 5% of the grade.
Oh, why am I doing it? No, I'm just kidding. I'm just kidding.
One semester I made it worth 0.
Really?
Nobody did it. Everybody died in the first test.
I would
That was my
imagine.
second semester teaching. I was like, why should homework hurt somebody twice? I'm not going to make it worth anything.
You should make it
Nobody
0,
did it.
but not tell anyone until then.
Well, that's what I basically do. I make it 5% and I don't tell anybody until,
Yeah.
I suddenly decided. Let it be known. So, let me see. So, I can figure out something here. This won't quite be correct. Shit, this might be something I can't really do as on the fly as I want to. Just to give you a rough estimate. If you make something on the test to say about where you are, right?
Yeah.
Then you will try to make an A.
Yeah.
A minus would be okay, or A?
A minus. I don't care.
Okay.
B plus would be fine too.
Was this the handout from Thursday? Professor, was this from Thursday last week?
That's the updated homework.
Okay,
Yes.
yeah.
There's
I wasn't
another
here last
handout for the power series stuff.
I got that one. I, just,
You got it?
I wasn't here Thursday, so I got this one.
Okay. Wait, I got so much going on in my head. Oh yeah, that's Jeff. You can do it, buddy. So you would have to average this on everything left. To
Like
make
my
it
test?
A minus.
Okay.
On everything left.
So 2 tests and the final.
Yeah. Not
I mean, that's
impossible.
not impossible now.
And you've corrected everything you can. So you've already got kind of like a fudge factor. So, if you got like a 89.7,
It's the same.
roughly
It's
the
the
same.
same. Okay, thank you.
Sure.
Can I get the first handout? I think it was 6.1.
Oh, the Power Series review.
Yeah.
Let me see if I got any copies left. I might have to give you the one I wrote on.
If not, that's okay. I can just use my book.
I had some right here. Probably remember the back of it. I'm eternally in search of paper.
I see paper rules your life.
Yeah, paper does rule my life. Oh man, I'm not gonna find it. I'm sorry.
Yeah, it's fine.
I just need to remember. I really need to be better about putting stuff up in Canvas. I just don't even think about that, to be honest. But you can email me, or I can shoot. I can shoot you one, or you can tell me to put it up in Canvas.
Okay.
It's just sorry, man.
No, that's fine.
All right.
Thank you.
Sure. Oh, here it is. Right. I knew that was gonna happen. So it's kind of written on it.
But that's okay.
It'll work.
Thank you.
Sure. Oh, that's.